Hey everybody, it's me again. We're going to do some more linear algebra. Today we're going to talk about the matrix equation AX equals B. And the reason we want to do this is we want to be able to represent systems of equations in a nice little compact way. So if you can, recall from our last video, we had span meant linear combinations. And linear combos, after some manipulation, I was able to write those as linear systems of equations. And what I'm going to do today is I'm going to use those same ideas that we had at the end of the previous video. I'm going to do some manipulations, and I want to express a system of equations in a nice little compact form. So now that we have vectors and linear combinations, we are pretty much good to go, except, do you remember like when we talked about properties of vectors, we did a lot of like scalar times a vector, vector plus a vector, but we never did vector times a vector. So that is the missing piece for a puzzle, and that is what is in our little green box of information today. We have a definition for a matrix times a vector. So we're going to start off with A is an m by n matrix. That means A has m rows and n columns. So m rows is going to be this way. And then n columns would be this way. And then we're going to have a V, and it is going to be an Rn. So V is going to be a column vector with n entries. So now what we're going to do is we're going to write A in a nice little compact way, where we take the first column and we write that as a vector, A1. And then we'll take the second column and we'll call that vector A2, all the way up to the nth column. So, quick question about A1. We're going to do a note. How many entries does A1 have? Well, we know that we have m rows, which means we have to have m rows in A1. That means A1 is going to live in Rm. And that's not unique to A1, that's all of them. So we'll say AI lives in Rm. Okay, now we've made it all the way up to this word and. So we have a matrix A and a column vector V, and we have the matrix product. The way we do that is we take the first entry of V and we multiply it with the first vector in A. And so you get this term V1 times A1, where A1 is a vector and V1 is a constant. And then you do that all the way up here until you hit Vn times An. So that brings us to our second note, so note 1, then note 2. A has to have the same number of rows, columns. There were n columns, as V has entries. If A has too many or too few columns, then you're going to run out of space over here with V or something, and things aren't going to match up. Okay. Does this look familiar? Hopefully, maybe it does. Maybe it looks like a linear combination from last time. Hopefully now that I've said it, you can be like, oh, okay, I see we have a constant times a vector plus a constant times a vector. Yeah, okay, linear combination. It's like it's all connected. It is all connected. But before we get into like properties of matrix vector multiplication, we are going to do an example where we run through this calculation. Okay, so we want to find this matrix vector product. Very first thing that we're going to do is we're going to take the first entry of V, multiply it by the first column of A. Then second entry of V, second column of A. And then last column of V, or last entry of V, last column of A. And then we have the power of matrix or vector properties on our side. So we can distribute that. And we can distribute it here too. I'll leave it as a minus. 2, 5, 8 plus 6, 12, 18. And then in the very end, now we can use vector addition, and we're going to get 7, 19, 31. Okay, beautiful. That's a lot of steps. We can do this a little bit more concisely. So we could just take the first entry here, and we can just multiply it against all these guys because we know where this is going, sort of a thing. So let's go ahead and do that. So more concisely. I can spell, it's a thing. Okay. We're going to do 3 times the first column. And then we're going to do -1, so the second entry, times the second column. Minus, we'll do plus, -1 times 2, plus -1 times 5, plus -1 times 8. And then the last one, 2 times 3. I am not being consistent. I will try and be consistent. 2 times 6, 2 times 9. There we go. And then can simplify that to 3 minus 2 plus 6, 12 minus 5 plus 12, 21 minus 8 plus 18, which gives us the same result. Okay, I'm going to put a star next to all these equal signs real fast. Note that I am not using the arrow that I used before. Equals, not that. We use equals when our matrices are equal. We use the arrow when we are like doing Gaussian elimination, so we are manipulating it. They end up being equivalent, but we don't want to, but we have done something to the matrix to make it look different. That isn't just like distributing and adding. Another way to think of it is for all of my legal people out there is, let's say we have our matrix A. Matrix A has rows 1, rows 2, blah, blah, blah. So when you multiply your vector, if you wanted to start getting fast at it, we're going to say this guy's our vector. You just take the vector and you rotate him like this. And then he's going to multiply across all those entries like that. So Gaussian elimination and matrix multiplication, those are two things that you are going to learn to turn the crank on very quickly. They are kind of boring, but you need to take a moment and get a lot of practice in. Okay, so now what we're going to talk about is properties of matrix vector products. I'm going to go through them pretty quickly. We've got, you can distribute a matrix over two vectors like this. It doesn't matter which one you do first. You can add them first or you can multiply it out first. Doesn't matter. A constant times a vector can be moved out to the front of the matrix because it gets applied to every entry. If you have a matrix times a vector of zeros, you're going to get a vector of zeros. And then last of all, we kind of touched on this. We have, if A is an m by m matrix, I'm going to try and write this out to help. So A is m by n, and V is a vector that is in n. That means it has n rows and it's one column, and so we can use the same notation here. You could kind of think of a column vector as being a matrix with one column. The product is going to be in Rm. So this is equal to A time, or don't use that. A, V together is going to be in Rm, which is the same thing as saying it has m rows and it is one column. That ties back to what we did on the very first page when I was like, where does AI live? Here, let's flip back. Where do these guys live? It's this comment. So when you have A1 times V1, that's going to live in Rm. And when you add up all these vectors that live in Rm, the result is going to be in Rm, which brings us to that statement right there. So a quick check to make sure that you're doing things right before you start trying to do multiplication that's impossible is you want to make sure that these guys are the same. Because remember, you need A to have the same number of columns as V does entries. And then the result is going to be the two outside numbers. So m by 1. And then just like vector properties, you can verify any of these properties by doing it component-wise. Okay, so last one, I want to define identity matrix for you. So identity matrix times a vector just gives the vector back because this one was 4, this one is V. Our note is the identity matrix looks like ones along the diagonal with zeros everywhere else. So like you'll have a 1 all the way down to this last one, and you'll have zeros all in between. So that's what the identity matrix looks like. All right, how does that help us with systems of linear equations? So glad you asked. We're going to take this system of linear equations and we're going to write it as the matrix equation AX equals B. Now, I'm pretty sure that you can tell what B is going to be. We've got B is on the right-hand side. More likely than not, he's going to be, I don't like that at all. There we go. It's going to be this over here on the right-hand side. So let's go ahead and try and do that. We know we have vector, we'll say 5, 2, -7 on the right-hand side. I'm going to say, well, I know 5 is equal to 3x1 minus x2 plus x3 from the very first equation. So I'm going to write a vector on this side that will be equal to that vector using the equations that we had. So the first entry of this matrix, or this vector, has to be equal to the first entry of our other vector. And then we can say x1 plus x3 is going to have to be equal to 2, so that is our second entry. Then we have negative 2x1 plus x2 minus x3 will be equal to 7. And now back to last time when we did span and linear combinations. We're going to kind of do what we did there in reverse. Like we kind of like ended up gluing things together. Now we're going to take things apart. What I mean by that is we have this vector, and I'm going to say I can write this vector as a sum of vectors instead of one vector, like this. There we go. And then I'm going to take it a step further, and I'm going to say I can factor out that x1, x2, x3 thing that I have going on in each of these vectors, because the first vector has an x1 in common with all of its terms. There we go, x1. 3, 1, negative 2. Plus, and then we'll factor out an x2, negative 1, 0, 1. Factor out x3, 1, 1, negative 1. So what is this? What did we talk about on the first page? Talked about matrix vector multiplication. We have a constant, or not a constant, but we have a number times a vector, times a vector, all the way down, number, vector. That means we can rewrite this, we can basically undo our matrix multiplication so that all these columns right here, these columns are my A columns. So 3, 1, negative 2, which means the next column of A is negative 1, 0, 1, and the last column of A is 1, 1, negative 1. And that's all being multiplied by the column vector x1, x2, x3, and that is equal to our B vector, 5, 2, 7, just like we knew it would be all along. So this is our B vector. This is our X vector. This is our A matrix, where A is the coefficient matrix. Yeah, we've done a lot of stuff with augmented matrices, and we finally get to use the coefficient matrix now. Notice here that X is a vector of variables. Now, what we can do is, instead of asking what is the solution to this system of linear equations, now we can ask, let's see. So now we can ask, does there exist vector x such that ax equals b is true? Okay, so the only thing new that we've learned is how to multiply that vector and that matrix together. That is the only new math. This is the same way to ask the question we've been asking all along. Can we solve this system of equations? It's new notation, that's it. So I've summarized that here in this lemma. Ax equals b has a solution is the very same thing as does this augmented matrix here in 3 have a solution, because we know from day 1 that we can solve a system of linear equations using an augmented matrix. And then day 2, we learned that span was the same thing as linear combinations, which is the same thing as the augmented matrix, which is this guy right here. So if AX equals B has a solution, the linear combination has a solution, which means the augmented matrix has a solution. These are all equivalent statements. Okay. So fun fact, just to summarize, AX equals B, we're solving this, is the same thing, or equals checking if B is an element of the span of the columns of A. Why? Because checking if B is in the span of some columns is the same thing as checking if this augmented matrix has a solution. Checking if an augmented matrix has a solution is the same as solving a system of equations, which is the same thing as solving the matrix equation. So here we go. We have like a bunch of different ways to ask one question. Isn't this fun? Next question. So, can we say that every B in Rm is also in the span of A1, A2, An? Let's translate, let's use all of our above translations that we just got. This is the same thing as asking, not sure if you remember this, and so I'm going to mention it right now. If every B was in the span, then the span would be equal to the entirety of Rm. And so now that is equivalent to asking, and that's a question, does AX equal B have a solution for all B's? And then this is the same thing as this augmented matrix. So does it have a solution for all B? Well, not necessarily. Remember first day, pivot points? I'm going to say not if there's a pivot point in the last column. Okay, so then what conditions do we need in order to get it to have a solution for all the B's? When is that going to happen? Well, it's going to have something to do with pivots. And so we're going to look at this example and we're going to try and find all the pivots for this augmented matrix. Remember, you can't just go around and find all the leading terms and be like, all right, those are my leading terms, those are my pivots. That's not how it works. You have to put it into row echelon form first. So let's do that. First thing I want to do, I want to remove him. He needs to go. So we're going to modify row 3 by subtracting 4 times row 1. And that's going to give me row 1 stays the same. Row 2 stays the same. And then row 3, let's see, 4 minus 4 is 0. And then we're going to have a 2 plus 4, negative 2 plus 4, positive 2. 26 minus 16 and then B3 was there before, and we are subtracting off 4 times B1. There we go. Okay. Now we're going to do this again, except now we want to remove this 2 here. We're going to remove him, so modify row 3 by subtracting off 2 times row 2. So row 1 stays the same. Row 2 stays the same. Row 3 is going to change. 2 minus 2 is 0. 10 minus 10 is 0. And then we have what we had before, B3 minus 4B1. And now we're also subtracting off 2 times B1. Or 2 times B2, my bad. Okay, so if we want this to be a solution, we need this to be 0 because we don't want it to be a pivot. Okay, so that's cool. Now we just have to find the right b's in order to have a 0. I'm sure there are lots of those, but I'm not interested in lots. I want all of them. If all the combinations is what I mean by all of them, all the b's. So we know this vector is in R3. That means B3 would be 1 and the other 2 are 0. That would mean that we don't get this equals 0 that we want in that. So that is an example of a B in R3 that is not going to work for this. So not all the B's work. How do we make it work? We need this to not happen, because we can't guarantee the right-hand side is going to be equal to 0 for all of them. We can always come up with a combination that's not going to be 0. So we want this 0 thing that's happening over here not to happen. And if we don't have a row of zeros, that means we need a pivot in that row. So that means AX equals B has a solution for all the B's in RM is the same thing as A has a pivot in every row. Okay. So this is basically another way, or another statement that is equivalent to the statements that we had in the previous lemma. And that's going to be all summarized in this nice theorem that has a name because it's so important. It's called the equivalence statements of A. The following are equivalent. We have AX equals B has a solution for all the B's in RM, which kind of comes back here to this lemma, is this one. That's the same thing as saying B can be written as a linear combination, and every B in RM can be written like that. So this guy always having a solution means we can always find a linear combination. And that is what we have here. That's our linear combination line in our little lemma. And then the columns of A span RM. That falls out because linear combinations, being able to find a linear combination means it's in the span. If B is a linear combination, B is in the span. So 2 implies 3. But we know now from the last example that 1 implies 4. If we have a solution, we have a pivot in every row. Or if we have a solution to all of them all the time, A has a pivot in every row. So that's the big theorem that we were working up to today. These 4 statements are all equivalent, and we're actually going to keep building on these throughout the semester. But that's all we have for now. Forgot to point out real quick, A is the coefficient matrix, not the augmented one. I know I said it earlier, but I wanted to highlight that here at the end. So there's your warning. Bye.